Hello. Today I'm going to be talking about Lab 3 for auto controls, position control of DC brushed motor in Simulink. Again, the objectives for this particular module are to work with Simulink, and then in this particular lab to learn the fundamentals of PD and PID controllers, learn about methods for tuning and testing, and then to implement these PD and PID controllers on the simulated brushed DC motor system. So to start off with, I'm going to take sort of a look at the model that I created and then look how to transition it from the speed control model into the one that can be used for position control. So this one here has a couple of changes. So the one used in speed control is here, which has the standard PI controller and the same plant as well as noise and disturbance inputs. And everything here is pretty much the same except for a few changes. And the first big one is in this PID block. The PI that was previously set to PI is turned to PID, and that allows you to have multiple controls so that you have all of the parameter tuning for the PID as opposed to just a PI controller. The plant is going to remain the same. Saturation block is the same. You're going to be changing up objects within your function generator, but the block itself is the same. There is an integrator block that is placed in between the summer block, which tells you the omega, into theta, translating from a speed into the angular position. But the rest of the model itself is the same. Now I'm going to start by walking through the procedure. So first off, we're looking at the PD controller qualitative analysis section. So within the proportional controller, the first step is, of course, to make sure that everything is set to its default. So your pulse generator is set to 0, your noise is at 0, your signal generator amplitude can be set anywhere from 1 to 3, maybe up to 5. For your PID controller, for the proportional control, this first section 2.1, you have your 0.1, your 0, 0, filter coefficient, and then you have your 1 for BSP. You have your response. And then the next steps are walked through. So when you start increasing KP, what's going to happen? I could demonstrate that by just, increasing KP. And we could see that underdamped response sort of occur. When we move on and we start looking at the PD control, we will start by changing those parameters. And so in this case, you'll start with like a KP of 2, and then we'll increase KD. And when we do that, we can see the more damped response. In the next section, we experimentally verify the controller gains that were designed for in the pre-lab. So in the case of the PD controller that you calculated, throw in those parameters. And we can observe the response. Make sure that when you do run these tests that you analyze and measure using the built-in tools available so that you can measure the responses. Again, here's where you can find your cursor and you can adjust your settings so that you're measuring between the different values. In the next section, we investigate tracking different waveforms. So the first one that we're looking at is the sawtooth waveform. Make sure you increase your amplitude. In my case, I go to -20. And then when you set your PID controller to whatever is stated within the procedure, in this case I'm looking at the results from the pre-lab, and you can observe the response. And specifically, you're going to be looking at how well does it track the steady state error on this waveform. So you could do that by measuring between those two waveforms. In our case, it's sum2 and theta at the same point in time. In the next section, we're going to be looking at tracking the sine wave, in which you can adjust it within your signal generator and make sure to also change your amplitude. And when you do that, you're probably going to be checking for the same controller, but remember to change those parameters. And then when you run it in the scope, you can check different things. In our case, we are going to be primarily focusing on the change in phase. And so in order to do that, you're going to want to go into your cursor, make sure you're checking between the two different thetas, and try to find your values by shifting around your time. So make sure that you calculate this and observe what happens when you change the different parameters. In the final section, we'll be looking at the response to disturbances. And so in order to do this, we want to first set the amplitude to 0 for the input, and then go to the pulse generator and input an amplitude, in this case 50, in order to observe what happens to the system given a steady state input when a disturbance is applied. Running it with your values that are from your pre-lab, you can sort of see the response and see how a PD controller will respond to this. You will then go in and analyze it with a PID controller and see how this may be advantageous to use a PID over a PI or a PD controller. As a final overview, I just want to remind everyone that in your IEEE report, you're going to want to include an explanation of your Simulink model, as well as the walkthrough of the procedure for each one of the individual steps and your results, and then provide a discussion as to why these results make sense and how this may influence your decision to use different controllers for different applications.